Okay, our next topic will be on cloud and virtualization. So generally, when we are talking about the cloud, we're talking about three things: the data center, cloud computing or cloud services and virtualization, and virtual computing. Though data center can be smaller, they generally large facilities which provide massive amount of power, cooling, and bandwidth. Only very large organizations such as Facebook and Google can afford to build their own private data center to provide services to their users. Other smaller organizations list space from a data center. Cloud service providers such as Cisco or Amazon Web Services or Microsoft Azure offer services out of the data centers. There are two basic types of clouds: public clouds and private clouds. Public clouds offer services and application to generally population, whereas private clouds are intended for a specific organization or entities, such as the government, are only accessed by those private organizations. There are different categories of cloud services, such as SaaS or software as a service, refers to the demand software or subscription model where the license and delivery of the software happens through the clouds. You'll find this with things like Office 365 or Adobe Creative Cloud, or even computing gaming software in which access to the software happens typically through a web browser. The software is typically not owned by, rather leased. So PaaS, another cloud platform, is the PaaS or platform as a service, is where the cloud services provider provides the platform, like the Java or .NET platform for a developer to develop an application or app. This oftentimes involves providing databases and tools to developers so that they can quickly develop an application. Infrastructure as a service refers to the virtual computing that provide over the internet on demand. This virtual computing, such as virtual server, as well as virtualized storage and virtualized networking capabilities that can be provisioned, allocated, and supplied on the demand on as a need basis. So this virtualization ability to abstract or separate the operating system from physical hardware. To create the virtual computer, the dedicated physical hardware needs to be shared over the virtual computer. So in this slide, we see a Windows 7 virtual computer that is sharing a physical dedicated resources of the host computer. This is done through hypervisor. There are two types of hypervisor used in the virtualization. A Type 1 hypervisor known as a bare metal hypervisor and a Type 2 hypervisor known as a hosted hypervisor. A Type 1 bare metal hypervisor is a virtualization server. The hypervisor is the operating system that installed onto the hardware directly, after which virtual computers can be created. There are different types of Type 1 hypervisors such as KVM, Red Hat, Enterprise Virtualization, Xen, Citrix, Xen Server, VMware, EXI, VMware vSphere, and Microsoft Hyper-V. So a Type 2 hypervisor is known as an hosted hypervisor. In this situation, the hypervisor is an application or a program that is installed on the top of the host operating system. In other words, you install the hypervisor such as VirtualBox or VMware Workstation, Parallel, VirtualOC on the top of the host computer. You install VirtualBox, let's say, on the top of the Windows operating system, then you can create a virtual computers. In addition to virtual computing, we can also virtualize switching and routing. In this slide, we can see two VMware EXI hypervisor. The virtual computers are all networked together with the Cisco Nexus 1000V virtual switch. This virtual switch brings the power of the Cisco switch to the virtualized network environment. So cloud computing involves large number of computing connected through a network that can be physically located anywhere. So it provides really heavily on a virtualization to deliver their cloud computing devices. Cloud computing can reduce operational costs by using resources more efficiently. Cloud computing supports a variety of data management issues, enabling access to the organization data anywhere at any time. So streamlines that the organization is an IT operation by subscribing only to the needed services. It eliminates or reduces the need for on-site IT equipment, maintenance, and management. It reduces costs for equipment, energy, physical plant requirement, and personal training needs. It also enables rapid responses to increasing data volume requirements. So cloud computing with its pay-as-you-go model allows organization to treat computing and storage expenses more as a utility rather than investing in infrastructure. The capital expenditures are transformed into operating expenditures. So cloud services are available in variety of options tailored to meet customer requirements. The three main cloud computing services defined by the National Institute of Standards and Technology in their special publication 800-145 is as follows. So the software as a service, platform as a service, and infrastructure as a service. The software as a service is access to the services such as email, Office 365 that are delivered over the internet. So the platform as a service is access to the development tools and services used to deliver application. The infrastructure of the service is access the network equipment, virtualize network services, and supporting network infrastructure. So as shown in the figure, cloud services provider have extended this model to also provide IT support for each cloud computing services for businesses. So IT as can extend the capability of IT without requiring investment in new infrastructure, training new personnel, and licensing new software. These services are available on demand and delivered economically to any device anywhere in the world without compromising security. So, cloud with interactive components about the four cloud computing services that are available, which include SaaS, PaaS, IaaS, and ITaaS, SaaS. Software as a service is more application are delivered over the web to the end users. So PaaS, platform as a service where tools are used to deliver application and so on and so forth. So there are different cloud models, public clouds, private clouds, hybrid clouds, and community clouds. So the public clouds, these are application and services made available to general population. So services may be free or offered as a pay per use model, such as paying for online storage, uses of the internet to provide this kind of services. So the private clouds, this is an application and services intended for a specific organization or an entity such as the government. A private cloud can be set up using the organization's private network. Through this, can be expensive to build and maintain. A private cloud can be also managed by an outside organization with strict access of security. So the another cloud model is the hybrid cloud. It's made up of two or more cloud, for where each part remains an indistinctive object, but both are connected using a single architecture, such as uh, part of the organization has private and some part are public access. So the community clouds is just a community cloud is created for exclusive use by a specific community. For this example, such as the healthcare organization must remain compliant with policies and laws that are required special attention and confidentiality. So the term data center and cloud computing are often incorrectly used. So these are correct definition of data center and cloud computing. The data center typically is data storage and processing facility run by an in-house IT department or a leased offsite. So the cloud computing generally is an ops premise services that offers on-demand access to a shared pool of configurable computing resources. These resources can be rapidly provisioned and released with a minimal management effort. So the term cloud computing and virtualization oftenly uh, used interchangeably. However, they mean different things. So virtualization is just a foundation of a network of cloud computing. Without it, cloud computing, as is most widely implemented, would not be possible. The cloud computing separates the application from the hardware. So virtualization separates the OS from the hardware, and the various providers offers a virtual cloud services that can dynamically provision servers as required. For this example, such as Amazon Elastic Compute Cloud, a web service provide a simpler way to a customer to dynamically provision the compute resources they need. These virtualized instances of server are created on demand on an Amazon EC2. Next, to fully appreciate virtualization, it is first necessary to understand some of the history of the server technology. So this historically enterprise server consists of a server operating system such as Windows Server or a Linux server installed in specific hardware. As shown in the figure, all of the servers are RAM, processing power, hard drive space were dedicated to the service provider. The major problem of this configuration is that when a component fails, the system that is provided by the server becomes available. This is known as a single point of failure. Another problem was the dedicated server were underused. So this dedicated server often sat idle for a long period of time, waiting until there was a need to deliver the specific service they provide. This server wasted energy and took more space than was warranted with their amount of service. This is known as a server sprawl. So in this figure, it displays historic operation installation in 8 servers such as a web server, email server, SQL server, LAN server, DHCP server, Active Directory server, AAA radio server, and a network management server. The first 6 servers are Windows Server and the last 2 are the Linux servers. So server virtualization takes advantages of an idle resources and consolidate the number of required server. This also allows for multiple operating systems to exist on a single hardware platform. For example, in this figure, the previous 8 dedicated servers have been consolidated into 2 servers using hypervisor to support multiple virtual instances of the operating system. The hypervisor is a program or firmware or hardware that adds an abstraction layer on the top of the real physical hardware. The abstraction layer is used to create a virtual machine which have access to all hardware of the physical machine such as the CPU, memory, disk, controller, and the network interface cards. Each of these virtual machines runs a complete and separate operating system. With virtualization, enterprises can now consolidate the number of servers they require. For this example, it is not uncommon for 100 physical servers to be consolidated as a virtual machine on the top of the 10 physical servers that are using hypervisor. The use of the virtualization normally includes redundancy to protect from a single point of failure. The redundancy can be implemented in different ways. If the hypervisor fails, the VM can be restarted and another hypervisor. Also, the same VM can run on 2 hypervisors concurrently, copying the RAM and the CPU instruction between them. If one hypervisor fails, the VM continues running on the other hypervisor. The services running on the VMs are virtual and can be dynamically installed or uninstalled as needed. So the figure of hypervisor OS installation display the hypervisor structure on the two servers. The hardware component is at the lowest level of the hypervisor on the top of the hardware. The connected to the hypervisor are four instances of the operating system. For server 1, there are four instances of the Windows operating system. On server 1, about the four instances of the operating system are services for such as web server, email server, SQL, and file server. For server 2, there are two instances, the Windows operating system and two instances of Linux operating system. On the above, the two instances of the Windows operating system are services for DHCP server and Active Directory server. On the server 2, above the two instances of the Linux operating system are services using Regis server and the network management system server. So what are the advantages of using a virtualization? One of the most advantages of virtualization is overall reduce the cost. So which means less equipment is required, so the server consolidated at lower maintenance cost. It also less energy is consumption or is consumed. So consolidating server lowers the monthly power and cooling cost. So less space is required, fewer server, network devices, and racks reduce the amount of required floor space. So additional benefit, easy prototyping, faster server provisioning, increased server uptime, provide disaster recovery system, and then the legacy support. So to help explain how virtualization works, it is useful to use layers of abstraction in computer architectures. A computer system consists of the following abstraction layer uh, as illustrated on the figure. So OS, services, OS, firmware, and hardware. At each of this layer of the abstraction, some type of programming code is used as is interface between the layer below and the layer above. For example, the C programming language is often used to program the firmware that accesses the hardware. An example of the virtualization is shown in the figure. A hypervisor installed between the firmware and the OS. The hypervisor can support multiple instances of operating system. So in this figure shows an example of a computer architecture abstraction layers. So starting at the bottom, working with your hardware, such as the CPU, memory, NIC disk, your firmware, your hypervisor, above that the firmware. So there are three instances of operating system on the same level, and finally, above that is the services such as the web server, email server, file server. So type 2 hypervisor or just hypervisor is a software that creates or run VM instances. So the computer on which a hypervisor is support one or more VM is host on the machine. So type 2 hypervisor also called as hosted hypervisor. This is because the hypervisor is installed on the top of the existing operating system such as the Mac OS, Windows, or Linux. Then one of the additional OS instances are installed at the top of the hypervisor as shown in the figure. The big advantage of Type 2 hypervisor is just the management console software is not required. The Type 2 hypervisor are very popular with consumers and for organization experimenting with virtualization. A common Type 2 hypervisor include Virtual PC, VMware Workstation, Oracle VirtualBox, VM Fusion, and Mac OS X Parallel. Type 1 hypervisor, these are called the bare metal approach because the hypervisor is installed directly on the hardware. The Type 1 hypervisor usually used on the enterprise server and data center networking devices. With Type 1 hypervisor, the hypervisor is installed directly on the server networking hardware. Then, instances of an operating system are installed on the hypervisor as shown on the figure. Type 1 hypervisor have direct access to the hardware resources. Therefore, they are more efficient than hosted architecture. So the Type 1 hypervisor improves scalability, performance, robustness. So in this figure, it shows that Type 1 hypervisor, the bare metal approach, the server consists of a hardware layer. Above that is the hypervisor, and then above it, there are three operating system displayed, such as the Windows, Linux, and the Unix operating system. When a Type 1 hypervisor is installed and the server is rebooted, only the basic information is displayed, such as the OS version, the amount of RAM, the IP address. An OS instance cannot be created from this screen. So the Type 1 hypervisor requires a management console to manage the hypervisor. So management software is used to manage multiple servers using the same hypervisor. The management console can automatically consolidate server and power on or off the server as required. For this example, assume the server 1 in the figure becomes low on resources. To make more resources available, the management console moves the Windows instance to hypervisor on server 2. So this management console provides recovery from hardware failure. If the server components fail, the management console automatically and seamlessly moves the VM to another server. The management console for the Cisco Unified Computing System is shown on this figure. So Cisco Unified Computing System Manager provides management for all software and hardware components in the Cisco UCS. It controls multiple servers and management resources for thousands of virtual machines. For some management console, also it allows over allocation. That particular allocation is when a multiple OS instances are installed but their memory allocation exceeded the total number of memory that a server has. For this example, a server has 16 GB of RAM, but the administrator creates 4 instances of an operating system with 10 GB of RAM allocated to each. This type of over-allocation is commonly practiced because all 4 OS instances really require the full 10 MB of RAM at any moment. So in this figure, it depicts the moving of an operating system instance between two hypervisors from server 1 to server 2. So both server have a hardware layer, and above that is a hypervisor layer. So the server 1 shows 3 operating systems such as the Windows, Linux, and the Unix. An arrow depicts that the movement of the operating system from server 1 to server 2. So server virtualization hides server resources. This example is the number and identity of physical server, processor, and operating system from server user. This practice can create a problem if the data center is using traditional and network architecture. For example, virtual LANs used by VM must be assigned to the same switch port as the physical server running the hypervisor. However, VMs are movable, and the network administrator must be able to add, drop, change network resources, and profile. This process is difficult to do with traditional network switches. Another problem is the traffic flow differ from substantially from the traditional client-server model. So typically, a data center has considerable amount of traffic being exchanged between virtual servers, such as the east-west traffic. These flows change in location and intensity over time, requiring a flexible approach to require network resources management. So existing management infrastructure can respond to changing requirements related to the management of the traffic flow using the QoS and security level configuration for individual flows. However, in the large enterprises using a multi-vendor equipment, each time a new VM is enabled, the necessary configuration can be very time-consuming. Could the virtualization infrastructure also benefit from the virtualization? If yes, then how? The answer is found in how a network device operates using a data plane and a control plane, as discussed later on this chapter. So, a figure of a man sitting down, pretending to type on a virtual laptop, depicting illustration of the various businesses tasks it could accomplish, such as the email, bar chart, organization chart, and more. So last topic is will be the network programming or the programmability. So the network programming, SDN and controllers, this network programming is used to program and virtualize the network. So we're talking about protocols, programming scripting, data modeling, markup languages such as architecture, APIs, or application programming interface, protocols such as OpenFlow, protocol which all allows programming languages to control a forwarding plane of a switch or a router as well as con and RESTCon. So these programming languages such as C or C++ and Java, scripting languages such as Python, Ruby, Lua, data modeling languages such as Yang, market languages such as XML, architecture, APIs like REST, architecture API, and APIs used over the web browse, and the Java API with all of the libraries and pre-written classes block of codes. So this SDN or software device networking is an approach of the network where the network is software programmable remotely. So it involves the Open Network Foundation, which support the concept and development of an SDN. And also, it has been responsible for releasing the Open Flow Protocol or standard, which is protocol that separates the control plane and the forwarding plane in a switch and a router. It also listed here is a OpenStack, which is a software platform for cloud computing and cloud computing providing IaaS or infrastructure as a service, which means the availability to manage pools of processing power. So this virtualized servers and network storage on an as needed basis for the customer to a data center. So in this image, you can see a comparison between the traditional architecture and an SDN architecture. Notice how the traditional architecture, each device, device 1 and device 2 and 3, let's say their network switches, each device has a control plane and data plan. So configure those devices, you configure the control plane on each of those devices. In an SDN environment, you notice how control plane has a separated from the data plane. Now, the three devices, let's say there are three switches, could be controlled from a single control plane or from a single controller using an OpenFlow protocol. This way, the three switches can be programmed from a single point or single software program. In the image, you can see the example further. So in this case, the application has been developed using a Cisco 1PK Open Network Environment Platform Kit. The software has been installed, has been written, let's say C or Java or Python programming languages. The application can be programmed. The data plane and the three switches on device 1, 2, and 3 using the Open Flow standard. So the network controllers are SDN control plane devices which are programmable point of automation to manage, configure, monitor, troubleshoot the virtual and physical network infrastructure. This automates the configuration of the network infrastructure. So a network controller is just an hardware which locate the SDN control planes. For this example, A network controller used in an SDN might be an open daylight platform. The open daylight platform is an open source SDN controller platform. You could see in this example where the SDN controller works with an application to control the network devices here listed as device 1, 2, and 3 and the data plane. So the Cisco ACI, or the application-centric infrastructure, is just a Cisco approach for software-defined networking and network controller. It involves three main things: an APN, or the application network policy, the application policy infrastructure controller, in this case the APIC-EM, which is the enterprise model for APIC, and switches that are applicable programmable, such as the Nexus 900 series switches. So in this example, you can see how the Cisco APIC-M works. So the Cisco interface model is the SDN controller, which sits between the application, the policy, and the data plane devices, such as the device 1, device 2, and the device 3. So the network devices contains following planes. So it can be a control plane, the data plane, a control plane, and the data plane. So this typically regarded as the brain of the device. It is used to make forwarding decisions. The control plane contains two and layer 3 route forwarding mechanisms, such as routing protocols, neighbor tables, and topology tables. So such as the IPv4 and IPv6 routing tables. The STP, the ARP table, this information sent to control plane is processed by the CPU. So the data plane is also called the forwarding plane. So this plane is switch fabric connecting to the various space network port on the device. So the data plane of each is used to forward traffic flow. So in this example, I illustrate how Cisco Express forwarding uses the control plane and the data plane to forward packets. The Cisco Express forwarding is the bands layer 3 IP switching technology that enables forwarding of packets to occur at the data plane without consulting the control plane. The control plane routing pre-populates the forwarding information based on the table in the data plane. This control plane ART table pre-populates the agency table. So the packets are then forwarded directly to the data plane based on the information contained in the FBI and adjacency table without needing to consult the information in the control plane. To virtualize the network, the control plane function is removed from each device and is performed by centralized controller as shown on the figure. The centralized controller communicates control plane functions to each of the devices. Each device can now focus on forwarding data while the centralized controller manages the data flow, increases the security, and provides other services. As shown in the figure of the architecture for Cisco Express forwarding on layer 3 switch, the figure of the 4 rectangular at the top is a rectangular depicting the control plane. The control plane rectangle has 3 gears of control plane. The control plane and the word CPU. So below the control plane uh, are 3 more rectangles. From left to right, there are just ingress interface, the data plane, which is directly below the control plane, and the egress interface. So the 5 arrows below the control plane, the egress interface, the 5 arrows go to the left, to the right, which it's depicting an IP address packets. The arrow enters the ingress interface on the left and passes through the data plane through a figure that is the FIB and the adjacency table, and finally through the egress interface as they exit the diagram. Over a decade ago, VMware developed a virtualizing technology that enabled host operating system to support one or more client uh, operating systems. So most virtualization technologies are now based on this technology. The transformation of the dedicated servers to virtualized server have been embraced with and is rapidly being implemented in the data center and enterprise network. The two major architecture has been developed to support network virtualization, which is the SDN and then the ACI. So the software-defined network is just a network architecture that virtualizes the network. The Cisco application-centric infrastructure is just a purpose-built hardware solution for integrating cloud computing and data center management. These are some of the network virtualization technologies, some of which are included as component in the SDN and then the ACI. The first one is the open flow. This approach was developed at Stanford University to manage traffic between routers, switches, wireless access point, and controller. The open flow traffic is basic elements in a building SDN solutions. The OpenStack approach is just a virtualization and orchestration platform available to build scalable cloud environment, provide an infrastructure as a service solution. This OpenStack is openly used with Cisco ACI. The provisioning, the orchestration in the network and processing of automating the provisioning of the network components such as the server, storage, switches, router, and application. So the other components are just another components include interface to the routing system, transparency, interconnection of the lots of links, Cisco Fabric path, the IEEE 802.1 AQ, shortest path bridging. So those are some of the examples. So the SDN architecture is just an architecture. It's just a traditional router or switch architecture. The control plane and data plane function occur in the same device. So this kind of routing decision and packets forwarding are responsibility of the device operating system. The software-defined networking is just a network infrastructure or architecture that has been developed to virtualize the network. For example, the SDN can virtualize the control plane, also known as the control-based SDN. So this SDN moves the control plane from each network device to a control network intelligence and making policy making entity called the SDN controller. The two architecture are shown on this figure. So the SDN controller are logically an entity that enables the network administrator to manage and dictate how the data plane of the virtual switch and the router should handle network traffic. It orchestrates, mediates, and facilitates communication between application and then the network elements. So this kind of SDN framework is just illustrated on this figure. Note that the use of the application programming interface or the APIs within the SDN framework. This API is just a set of standard requests that defines the proper way for application to request services from another application. So the SDN controller just use the northbound APIs to communicate with upstream application. This API help network administrator to shape the traffic and deploy the services. So the SDN controller also uses a southbound APIs to define the behavior of the downstream virtual switches and the routers. So the API is just a set of standard requests that defines the proper way for an application to request services from another application. A flow, open flow is just originally a widely implemented south bound APIs. So the SDN controller is just defined that the data flows and occur in the SDN data plane. So flow is just sequence of packet traversing to a network that shares a lot of set of header field values. For example, a flow could consist of all of the packets with the same sources and the destination IP addresses, or all of the packets with the same VLAN identifier. This each flow traveling through the network must first get the permission from the SDN controller. If the SDN allow it, it flow and compute a route for the flow to take and add an entry for the flow in each of the switches along with the path. So the controller populates and the switches manages the flow table. So this each of the open flow switch connects to the other open flow switches. So they are can be interconnected to an end devices that are part of the packet flow. So to switch to the switch, a flow is just a sequence of a packet that matches a specific entry on the flow table. So as you see on the video, there are just very few organizations actually have the desires or key skills to program the network using the SDN tool. However, the majority of the organization want to automate the network, accelerate application development, and align their IT infrastructure to better meet the business requirements. So Cisco developed the application-centric infrastructure to meet this objective in more advanced and innovative ways than earlier SDN approaches. So this ACI is just a data center network architecture that developed by Insimi and acquired by Cisco in 13 rather. So Cisco ACI is just a purpose-built hardware solution for integrating cloud computing and data center management at a high level. The policy elements of the network is removed from the data plane. This simplifies the way data centers network are created. So there are just three major components of the ACI architecture. So these are the application network profile, application policy infrastructure controller, and lastly the Cisco Nexus 900 series switches. So the application network profile is just a collection of the end-to-end point group with their connection, and their policies are defines those connection. The application policy infrastructure is just a brain of all of the ACI architecture. It's just a centralized software control that is designed for programmability and centralized management. It translates application policies into a network programming. So the Cisco 900 series, Nexus 900 series switches, they just provide an application aware switching fabric and work with an APIC to manage the virtual and physical network infrastructure. So as you see in the image, so API is positioned between the AMP and then the ACI is enabled infrastructure. The API C translate the application requirements into a network configurable to meet those needs. So it's a fine lift technology. This is just a 6.0 ACI fabric is composed of APIC and the Cisco Nexus 900 series switches using the two-tier spine lift technology as shown on the figure. The lift switches always attached to the spine, but they're never attached to each other. Similarly, the spine switches are only attached to the leaf and the core switch, not shown. So in this two-tier topology, everything is one half from everything else. So this Cisco APICs and other devices in the network physically attach to the leaf switches. So when compared to the SDN, APIC controller does not manipulates data path directly. Instead, it centralizes the policy definition programs the lift switches to forward the traffic based on the defined policies. For virtualization, so ACI support multi-vendor hypervisor environment that would connect to the lift switches, including the following. So it could be Hyper-V, Azure Pack, Red Hat, and the like. So the figure shows the API spine lift technology at the top of the topologies is just a pine with two Nexus 9500 switches. Each of the switches are connected to the four Nexus 300 switches using a 40 gigabyte Ethernet links. So the 300 and 9300 switches are part of the lift layer. The four 9300 switches are just connected to a server labeled all other network devices using a multiple 10 gigabyte Ethernet link. So the diagram also shows the 9300 switches connected to a box showing that the word APIC with the symbol of a clock on alarm and a lock a person. So SDN types to better understand. So the APIC EM, it's very useful to take a broader look at these three types of SDN. So it's just a device SDN. The device are programmable by application running on the device itself or on the server in the network. So the Cisco one, PK, is just an example of the device-based SDN. It just enables the programmers to build an application to integrate and interact with the Cisco devices. So the control-based SDN is just uses a centralized controller that has a knowledge of all of the devices in the network. This application can interfere. This application can interface with controller responsible for managing the devices and manipulating traffic flow throughout the network. So this Cisco Open SDN controller is just commercially distributed of OpenDay Lite. Lastly, the policy-based SDN is just similar controller-based SDN where a centralized controller has a view of all devices in the network. That includes additional policy layer, uses a built-in application that automates advanced configuration tasks via a guided workflow and user-friendly GUI. No programming skills are required, but Cisco API CEM is also a requirement or example of this type of FDM. So the policy-based SDN is just the most robust, providing for a simple mechanism to control and manage policies across our entire network. So Cisco has controllers. This API EM features provide the following. It discover the device inventory, host the inventory, and then the policy. Policy, the topology, the policy analysis. So let's just discuss about the discovery. So discovery supports the discovery functionality that is used to populate the controller's devices and host inventory device database. So the device inventory just collect details of information for the device within the network, including device name, the device status, MAC address, IPv4 or IPv6 addresses, the version of the ISO, the what platform, how many uptime does the device boot, and then the configuration. The host configuration is just the host inventory is just a collection of detailed information from the host with the network, including the host name, user, MAC address, IPv4, IPv6 addresses, network attached point. So policy is just the ability to view the policy across the entire network using the QoS. So the topology it just supports graphic view of the network. So it's just a topology view. So policy analysis is just an inspection and analysis of a network access control policies. So this is just the ability to trace the application on a specific paths between end device to quickly identify the ACL in use and problem areas. So one of the most important feature of the APIC-M controllers is the ability to manage policy across the entire network. So policies operates a higher level of abstraction. So traditionally, the device configuration applies to one device at a time, whereas SDN application or policies apply to the entire network. So this APM ACL analysis path trace provide tools to allow administrator to analyze and understand the APL policies and configuration. This creates a new ACL or editing existing ACL across your network. To implement a new security policy can be challenging. So the administrators are hesitant of changing the ACL for fear of breaking them and causing new problems. So the ACL analysis and path trace allows the administrators to easily virtualize traffic flow and discover any conflict, duplicate, or shadowed ACL entities. So it also provides the following tools to troubleshoot the ACL entries, such as the ACL analysis. So this tool examines ACLs on the device, searching for redundant and conflicting or shadowed entries. So the ACL analysis enables the ACL inspection and interrogation across the entire network in exposing any problems and conflicts. So the ACL path trace, this is just a tool examining a specific ACL on the path between two end nodes, displaying any potential issue as shown on the screen. So this kind of screenshot of the Cisco APIC Enterprise Model or the APIC M software used to manage Cisco SDN controllers for enterprise networks. So the screenshot also display the APICM policy analysis page. So this screenshot is displaying the APIC ACL analysis trace path page. So as a summary of what we have discussed, so the IoT refers to the network of billions of physical objects accessible through the network as we continue to connect the unconnected. The challenge for IoT is just securely to integrate new things from multiple vendors into existing network. So there are 6 pillars of IoT. So the network connectivity, the cloud computing, security, data analytics, management and automation, application enablement platform. So cloud computing is just a large number of computers connected to a network that can be physically located anywhere. So this cloud computing with pay-as-you-go model is just allow organization to treat computing and storage expenses more as a utility rather than investing in infrastructure. So this cloud computing services includes software as a service, platform as a service, uh, infrastructure of the service, and IT as a service. This cloud models also includes public clouds, private clouds, hybrid clouds, and community clouds. This computing is just possible because of the data center. So a data center is just facilities used to house a computer system and associated component. So the data centers rely heavily on virtualization to provide cloud computing and services. This cloud computing separates the application from hardware and software. This virtualization separate the OS from the hardware. This allow cloud computing customers to dynamically provision the compute resources they need when they need them. So virtualized server hardware is just managed through a hypervisor. The Type 1 hypervisor is just installed directly on the hardware. Then the OS and the VM be installed. Type 2 hypervisors as the Mac OS Parallel or Oracle VirtualBox are installed on the top of any existing operating system. So the SDN is just a network architecture that has been developed to virtualize the network. So this SDN can be virtualized in a control plane, as also known as control-based SDN. This SDN moves the control plane from each network device to central network intelligence and policy making entity called the SDN controller. This SDN controller defines the data flow that occurs in the SDN plane. So there are 3 types of SDN. So the Cisco-based SDN, the controller-based SDN, and then the policy-based SDN. This policy-based SDN, such as the Cisco APIC EM or Enterprise Management, is the most robust and by providing for has simple mechanism to control and management policies across the entire network. What's the most feature of that controller is that the ability to manage policy across the networks. So that ends our chapter 7, and then I'll see you on the next chapter.